This is section 10.1, Trigonometric Identities. Now, we've already talked about a few of the identities that you should still know. So if you look at the first page or so of the slides that I've put in, first thing I want you to notice is there are a lot of identities, and you need to memorize them as we learn them, because you have a lot of memory work to do, because you are responsible for all of these trigonometric identities, and you will not be allowed a cheat sheet on a test. So the good news is that a lot of them are ones that you use often enough that they're not that hard to, quote, memorize, because your familiarity with them makes it so that memory work is, well, yeah, of course I know that one. And also, remember how to acquaint yourself with an identity and how you might build identities from other identities you know. So the memory work isn't necessarily straight up memorization for all of it. Some of it is a recognition of patterns. So I'm going to write the reciprocal identities. They're on your notes, but these are ones that you definitely are supposed to know. And in each case, each function has a reciprocal function. And you can write, for example, that sine of theta is the reciprocal of cosecant, or you can say that cosecant of theta is the reciprocal of sine. And both directions work, and both of these are true. And so we have 6 reciprocal identities. And I'm almost done writing them now. I might suggest flashcards or something like that to help you get these in your head. And I find that when I'm doing flashcards, if I will force myself to look at one side, write down what I think is on the other side, and then flip it over, if I get it, I put it in my I know this stack. And the ones that I miss or can't do consistently, I do them again and again and again. Just put it on the bottom of the stack, and when I get to it, I try it again. To me, that was how I memorized a lot of things, is with flashcards. Some of you might do better having a partner, and you say one side of the identity and your partner says the other side, and then you double check that you're right, sort of one quizzing the other. Okay, the quotient identities, which I sometimes might refer to as the ratio identities, there are 2 of them that I would like for you to know. Sine of theta divided by cosine of theta is tangent of theta, and cotangent of theta is cosine of theta over sine of theta, which of course is the reciprocal of sine of theta over cosine theta. A lot of these, you can kind of say them in several ways, and it's like, oh yeah, that means the same thing. So the fact that cotangent theta is the reciprocal of tangent theta, and if tangent theta is sine theta or cosine theta, that automatically means cotangent of theta must be the reciprocal of that fraction. So cosine theta over sine theta makes a lot of sense. The Pythagorean identities. I'm going to start now talking about how knowing some of the prior ones in this list means that you don't really have to have memorized all of the identities per se. You do have to have an idea of about what they are in order for this to work, but I don't think you have to necessarily truly memorize all of them. For the Pythagorean identity, the one that I memorized first is this one. And I found that if I know this one and I know the identities above, I can actually get the other two as needed from this one and the identities above. For example, I could divide everything in this original Pythagorean identity by sine squared, and I would get 1. And cosine divided by sine will give me cotangent squared, and 1 divided by sine squared theta will give me cosecant squared theta. And there's another identity. So I never memorized that one, to be quite honest. The second one there, I just know how to turn the basic Pythagorean identity into one of the other two. The other one I get by dividing everything by cosine squared. Sine squared divided by cosine squared will be tangent squared theta. Cosine squared theta divided by itself is 1. And 1 divided by cosine squared theta will be secant squared theta. And those are the 3 Pythagorean identities. The last 2 of which I use other things to develop them. I never actually memorize them. Then the even odd identities. This is the one that we kept adding to slowly as we were graphing. And then I summarized them for you recently. This is just a nice summary of all the identities, all in one place, the ones that we have so far. Well, I can't spell sometimes. I get distracted with what's coming next, and I forget to finish the word correctly. Identities, okay. I hope I didn't misspell that up above anywhere. Identities. Okay, no. That's the first time I made that mistake. All right, so the sine of negative theta is the opposite of sine of theta because it's an odd function. Cosine of negative theta is cosine of theta because cosine is an even function. Tangent of negative theta is the opposite of tangent theta, so it's an odd function. And if you'll recall, the odd functions, their reciprocals are also odd. So since sine is odd, then cosecant is odd. And if the function is even, its reciprocal function is also even. So the secant of negative theta is secant of theta. And of course, because tangent is odd, because tangent is odd, its reciprocal function is also odd. Okay, so those are the even odd identities. Now, there are times where an alternative form of one of these, particularly the Pythagorean identities, might be useful. For example, an alternative form of the basic one is you could solve that as an equation for either sine squared, which would be equal to 1 minus cosine squared, or you could solve the original one for cosine squared, which is the same thing as 1 minus sine squared theta. Those alternative forms are sometimes useful to know because you may have a 1 minus cosine squared theta and you need to realize, oh, I can put sine squared theta in its place. So you can solve the second one for either cotangent squared theta or for 1, and you can solve the third one for either tangent squared theta or for 1. And those alternative forms are ones that you would want to make sure that you're aware of for substitution purposes. Okay, so let's see what types of questions we're going to encounter once we know these identities and have them down pretty pat. And notice I'm assuming that you have them down pat. You've memorized them. You've worked with them. You have all of them pretty much at your fingertips, figuratively speaking. All right, so the first question of this type is to express one function in terms of another. Meaning, I want cosine of x equal to something, and the only trig function I can have is tangent x. I can't have any other trig function besides tangent of x. So, since secant is related to both cosine x and tangent x, related to cosine by reciprocal, and related to tangent with one of the Pythagorean identities, what I want to do is I want to start with the Pythagorean identity that has tangent in it, which is where we're headed toward, is something in terms of tangent, and how that's equal to secant squared x. 1 plus tangent squared x equals secant squared x. So I'm going to take the reciprocal of both sides of this equation. So 1 over 1 plus tangent squared x. And then if I take the reciprocal of secant squared x, I get cosine squared x. So I've taken the reciprocal of both sides. Then, to solve for cosine of x, I'll need to take the square root of both sides. Please don't forget you need to insert plus or minus whenever you take the square root of both sides of an equation. Looks like I need to expand my vincula, my two vincula, so that they're long enough to accommodate what we have. And of course, to simplify, we can split that radical into the square root of the numerator, square root of 1 is 1, over the square root of the denominator. And then we can't leave radicals in the bottom, in the denominator of a fraction, so we're going to multiply by 1 in the form of that radical over itself, which will leave cosine of x equals plus or minus the square root of 1 plus my pen is kind of faltering. 1 plus tangent squared x over, wow, my pen is really messing up. I'm so sorry. This doesn't look good. Well, whoa, what happened there? Okay, well, something's messed up. It's really goofy right now, so I'm not sure what's going on. Let me see if I can rewrite that. If not, this may be a place where I end this recording and just pick up with another one, because I may have a gremlin in my computer and I'm going to have to go exercise it perhaps. Oh, seems to be working. Not sure what that temporary glitch was. Okay, so anyway, once that's rationalized, you have cosine in terms of tangent x, and that one's done. Now, the plus or minus, cosine of x can have a positive answer in the first or fourth quadrants, or a negative answer in the second or third quadrant. So depending on what quadrant x is in will be as to whether you use the plus or the minus. It doesn't mean you get two answers. It means it's either positive or negative depending on the placement of x, what quadrant it's in. Okay, so write tangent of theta plus cotangent of theta in terms of sine and cosine. Okay, so tangent of theta is sine of theta over cosine of theta using the quotient identity, plus cotangent of theta is cosine theta over sine of theta. So to add fractions, we need to get a common denominator. Since cosine theta and sine theta are relatively prime, meaning there's no common factor, it's like if you were adding fifths and sevenths, like 2/5 plus 3/7. Those are relatively prime. And so the common denominator is simply the product of the two denominators you have, and you multiply by, in the first case, by 7 over 7 as a form of 1, in the second case, by 5 over 5 to get the common denominator of 35. That's what we're going to do here. We're going to multiply the first fraction by sine of theta over sine of theta as a form of 1. And we're going to multiply the second fraction by cosine theta over cosine theta. Okay. So that gives me sine squared theta over sine theta cosine theta, our common denominator, plus cosine squared theta over our common denominator, okay? Then we know the rule for adding fractions with the same denominator is to add the numerators and keep the common denominator. And then using the Pythagorean identity, we know that sine squared of theta plus cosine squared of theta is 1. And this is your simplest answer, 1 divided by sine theta cosine theta. That's our tangent of theta plus cotangent of theta in terms of sine of theta and cosine theta. So, hint for verifying identities. When they say verifying identities, most books call that proving identities. So I'm going to use those interchangeably. I think they're calling it verifying because it doesn't sound as scary, perhaps, as proving. But it's technically really proving identities, so that's what I'm going to call it most of the time. They may use the verbiage verify this, or use verifying processes to show that this is true, but whatever. That's the same thing as proving, which is what I'm going to say. So the hints for proving identities is, number 1, make sure you learn all of the fundamental identities, backwards and forwards and alternate forms and everything. 2, when you're trying to verify or prove an identity, you're going to start with one side or the other, which I'll show you in a minute. And typically, it's easier to simplify than it is to complicate. So start with the more complicated looking side of the identity that you're to prove and work on changing it until it becomes the other side. Third, usually any factoring or indicated algebraic operations should be performed. So you're going to be using identities for substitutions. You're going to be using algebra to do things like factoring, adding fractions like we just did, subtracting fractions, multiplying by a form of 1, and things like that. So make sure that you're able to do all of that algebraic stuff correctly. 4, As you select substitutions, keep in mind the side you are not changing because it represents your goal. So you're going to have one side that you start with, and the other side is where you're headed. 5. If a fractional expression contains 1 plus sine of x, or 1 minus sine of x, or 1 plus cosine x, or anything that's 1 adding and subtracting with a trig function, basically, multiply both numerator and denominator by its conjugate. And 1 plus sine of x times 1 minus sine of x, that part will give you 1 minus sine squared x, which you can then use as an alternative form of the Pythagorean identity and replace 1 minus sine squared x with cosine squared x to simplify. 6. It's sometimes helpful to express all functions in terms of sine and cosine and then simplify the result. That's kind of like the last-ditch effort. It's not what you want to try first, because there's usually a more elegant way to do a proof than to just convert everything to sines and cosines. All right, so we're to prove this identity. They say verify, but I'm going to keep using the word prove. Prove that cotangent of x plus 1 is equal to cosecant of x times the quantity cosine x plus sine of x. Okay, so the first decision is which side of that identity looks more complicated. Since I can't really talk to you right now and find out what you think, I'm going to have you think about it and then tell me what you think it is, but I won't hear you. So I'm going to go with what I think is most complicated. All right, so when we're doing a proof, verification, write the word proof. Okay, so this is the beginning of the answer. It's when you write proof. Underneath that, write whichever side you think is more complicated. I think the right side is more complicated. Hopefully you came up with the same side as the more complicated side. Now, in proving, you can only do one thing at a time, so it's going to feel a lot like you're taking baby steps. And that is exactly right. You do one thing at a time only. Otherwise, it's real hard to follow your logic and ascertain if it's really true or not. So don't skip steps. This is one of those times where you really need to show everything. All right, so I'm thinking of cosecant of x is the same thing as 1 over sine of x. So I'm going to use that reciprocal identity, and that's my one thing in this line. So I'm not going to do anything else except just copy down the rest of it. Okay, then algebraically I can distribute, so that will become cosine x over sine of x plus sine of x over sine of x. Now look at the top, look where we're headed. We're headed for cotangent x plus 1. That's what we want to see. So if we're not headed in that direction, we probably need to back up and try something else. But as it turns out, this is actually good. It's working really nicely because cosine x over sine of x is cotangent of x, and sine of x divided by itself is 1. And so we now have the other side of the equation that we've shown is the same thing as the left side. Once we've done algebraic and trigonometric work on that one side, we turned it into the other side. Notice this is not an equation to solve. You can't do stuff to both sides. That's not what this is. We're trying to prove that it is an equation that's true. And so if you do stuff to both sides, you're already assuming that they are equal. If you want to add 7 to both sides, you can only do that if you have equality to begin with. And the equality is what we're trying to prove. So when you're doing these proofs, do not try to do something to both sides. That is not valid, and it will not receive credit. So please pay attention to that. So then the conclusion is, therefore, that's what those 3 dots in a triangle mean in a mathematical way. Therefore, we've just proven that the cotangent of x plus 1 really is equal to the cosecant of x times cosine of x plus sine of x. Okay, so let me give you sort of an overview of how these proofs will always work and how they should look. You're supposed to prove, for example, that A is equal to E, where A and E are just expressions. I'm just simplifying. So we're going to start with whichever of those two that we think is the more complicated. And I'm going to assume this time that A is the most complicated thing. So I'm going to do something like a trig substitution or an algebraic step and change that into B. Then to B, I'm going to maybe do an algebraic thing or a trig substitution and turn that into C. And I'm going to keep doing that, turn that into D, and then turn that into E. And notice that now I have, with a string of equal signs, if A equals B, and B equals C, and C equals D, and D equals E, what does that prove? What proves that what you started with is equal to what you ended with. This is a proof of transitivity. It's a transitive proof because we're using the transitive property of equality. So the technique we're using for these is called a transitive proof. And you remember the transitive property of equality. If A equals B and B equals C, then what's true? Well, that A equals C. That's the transitive property. This is just extended where A is equal to something, which in turn is equal to something else, which we called C, which is in turn equal to something else, which we call D, which in turn is equal to E. And oh, that's what we wanted to prove A was equal to. And we can then say that, therefore, A is equal to E by the transitive property of equality. That's what's behind all of these proofs. And notice the format. You start with one side A, and in the same line write equals, and then change it somehow, like with a trig identity or an algebraic manipulation. And then below that, equal, equal, equal. Those are all lined up until the right side of the original problem is what you end up with. And then you can draw the conclusion that the left side in this case is actually equal to the right side. Therefore, A equals E. All right? So that's how these proofs will look. So kind of memorize that format. That's what you're going to want yours to look like when you're doing these proofs. Okay. So let's do another one. We're going to prove that this equation is an identity. Okay, so prove that tangent of t, and by the way, the variable theta is not what the argument has to be. You can have lots of different variables used. Theta is probably the most prevalent one, but using t is also possible. So you're going to see different variables used today. So this is worthy if you're paying attention to and realizing that this is a possibility, that the variable might not be the variable that you like best. Okay, so secant squared t minus cosecant squared t. All right, so we start out with our proof, and our decision is which side of that identity looks more complicated. And my thought was the left side was more complicated. That doesn't mean that you couldn't have chosen the other side, by the way, and gotten the right answer going from the other side instead of from this side. It is definitely possible. In fact, there's some where it's a real toss-up as to which side is more complicated, And so you just pick one because there's really no difference between them. One of the algebraic things that you might see yourself using is the idea, these are going to be ideas over here to the right of things that you might use, that if you are supposed to add or subtract fractions that have the same denominator, that means that you add or subtract the numerators and keep the common denominator. The use that we'll a lot of times put that to is the reverse is also true. If you have a binomial, or it can be longer, it could be a trinomial, whatever. But if you have a binomial over a monomial, you can take each term of the polynomial individually over your common denominator and put plus or minus signs in between those fractions. So that's what I'm going to do here is algebraically, I see that I can split this into two fractions. Oops. Okay, let's see. Now what? Write the equal sign below the previous one. And let's see, what can we do with that? Well, if I wanted to, and this is another property, if I have A multiplied by B over C, you can put the A over 1 in your head if you want to and multiply A times B over 1 times C. So that's something that can be done, and it's reversible if need be. And that's what I want to do, is I want to use that idea, that reversal idea down here. So I'm going to put the tangent T out in front, like the A, which would leave a 1 in the numerator over sine T, cosine T. And then I'm going to do the same thing for the cotangent of T, pull it out in front, and it will be multiplied by 1 over that common denominator. Okay. Now, I can then, if I want to, change tangent of T into sine of T over cosine of T using the ratio identity. Not the ratio. Yeah, that's why I call it the quotient identity. It's what your book calls it. Told you I'd probably slip and say that. And then what would cotangent of T be? Well, it's cosine of T over sine of T. Okay. Now, in doing the multiplication, you might notice that this in the first multiplication, that this sine of T and this sine of T cancel. And what's left when those are canceled is 1 in the numerator and cosine T times cosine T. In other words, cosine squared T. Minus, and you might notice in the next multiplication problem that this cosine T cancels this cosine T. Notice that I'm not obliterating and drawing over that so I can't see what was there, because I'm going to grade every step of this work, so please don't obliterate things. Underlining, excuse me, checking, or a faint line through things you're canceling is fine. Just don't draw through it so I can't read it. So you're left with 1 in the numerator and sine times sine, which is sine squared of T. Well, using the reciprocal identities, I know that 1 over cosine squared is secant squared t. And I'm continuing to look at the other side of the equation in the hopes that I'll land there. In fact, this is looking pretty good. 1 over sine squared is cosecant squared t. And what were we aiming for? Secant squared t minus cosecant squared t. Hey, that's what we got. All right, that means we're done. Therefore, we now know for sure that tangent of t minus cotangent of t over sine t cosine t is indeed equal to secant squared t minus cosecant squared t. Okay, so that finishes up that proof. A couple of remarks I want to make. Not every proof will look the same, and yet they can all be equally valid. Someone may have thought of a different way of doing this, doing one step at a time and showing all their work that's perfectly legitimate and will get full credit, and it might not look exactly like mine does right here. So that's my first point, is there's not necessarily exactly one correct answer. My second point is, and this will bolster what I just said too, is that I may choose to start with the left side, you may choose to start with the right side, which means our proofs may not look very much alike at all, but they could both be valid. So please keep in mind that I'm looking for a proof, but it needs to flow logically from step to step to step, doing one thing at a time. Like in this step where I crossed out the sine t's and crossed out the cosine t's, that's really the same idea twice. So it's okay to do both of those in the same line because it's really the same idea. But don't skip a whole bunch of steps and expect to get full credit, because it just won't work that way. All right, so we finished that one. And let's do another one. Okay, so I'm going to move over a little bit. And move up a little bit. Over to here. There we go. And let's just work on the next one. Okay. Oh, and the other thing I wanted to mention is all of these that we've proven today are not to be memorized. Okay, I want you to memorize the basic fundamental identities, and I'll tell you when there's more to go. And basically, if it comes in a set like the odd even identities or the reciprocal identities, those are ones to memorize. If I've asked you to verify or prove an identity, that one is not to be memorized. So don't think that you have to memorize all those. That's a lot of extra that I really don't want you to do. Okay, so we're going to prove. And I really would like for you to try this on your own first. So after I've written it down, pause and see if you can work it by yourself. And then see what happens when I try to prove it and see how you did. Keeping in mind, if yours doesn't match mine but is logically sound and goes through this steps one at a time logically, I think you're going to be fine. Okay, so pause it now and see if you can prove this identity. Okay, hopefully you did well. Those two sides of that identity to me are, well, about equally difficult. I don't think there's one that really stands out as a way better one to start with than the other one. So I'm going to just pick a side and go with it. I'm going to pick the right side. You very well could have picked the left side, and your process would be looking different, but you'd end up with the correct answer, I'm pretty sure. Okay, so in this first step, what I want to do and I think I said this before, but let me say it again. If you see 1 added or subtracted with a trig function, a good idea to try is to multiply by 1 in the form of the conjugate of that binomial over itself. So the conjugate of 1 plus sine x is 1 minus sine x. By the way, had you started with the other side, my suggestion would have been the same. If you had started with cosine x over 1 minus sine x, I would have suggested that you multiply that by 1 in the form of 1 plus sine of x over 1 plus sine of x. So you could see how it wouldn't really matter which one of these you started with. You end up kind of doing the same idea. Okay, so when you multiply conjugates, this is another algebraic thing. So let me put this in a little box over here. When you multiply conjugates, a plus b is the conjugate of a minus b. If you want to think through that on your own first, pause me and then come back. Every time you multiply conjugates, you will get what's called a difference of 2 squares, because the negative AB and the positive AB that you get for the outer and inner products adds up to 0. So you only get first times first and last times last. And so that's also, by the way, reversible. If you have a difference of 2 squares, it can be factored into the product of conjugates. We may see that, we may not, I don't know, but it is a truth as well. But right here I have 1 plus sine x, a plus b times 1 minus sine x times a minus b. So what I'm going to get out of that is 1 squared, which is 1, minus sine of x squared, so sine squared x, over cosine of x times 1 minus sine of x. Okay. Now, I hope that you've memorized all of your identities. This is an alternative form of the first Pythagorean identity, and it's the same thing as cosine squared x. And that's one of those things I would hope that you would learn to recognize and substitute correctly. Divided by cosine x times 1 minus sine x. You might notice, since we started with the right side, I'm looking for the left side to pop up, and that left side has a 1 minus sine x in it, so I don't want to distribute that cosine x through because I want that 1 minus sine x to be visible in the end. And in fact, in this very next step, that's going to happen. You have cosine times cosine in the numerator. If you cancel one of those cosines with the denominator cosine of x, you'll still have 1 cosine of x in the numerator and none of them in the denominator, which leaves you with cosine x over 1 minus sine x, which is the other side, and therefore we've proven what we set out to prove. Therefore, we know that 1 plus sine of x over cosine of x by transitivity is really equal to cosine of x over 1 minus sine of x. There's something that you might see done, especially in the textbook examples, where they over to the side will tell you what they're doing each step, kind of like a justification. And I know in geometry you probably had to, if you did a proof like this, you had to provide justifications for every step. And I guess technically we could do that here too, but I don't really want to mess with writing those down, nor do I want to grade them when you write them down. So for me, it's simply, I should be able to follow the logic. When I look at something that looks like what I see right now on the screen, I should be able to follow the logic of what happened as you went through that. It should be clear. But I've been stating what I'm doing. In the first case, I multiplied by 1 in the form of the conjugate of that binomial over itself. Then I got a difference of 2 squares in the numerator and just multiplied the two denominators. Then for the next one, I used an alternative form of the Pythagorean identity and replaced 1 minus sine squared x with cosine squared x. And I used algebraic techniques of canceling to get rid of that cosine x in both numerator and denominator. And then the last step is true because of the transitive property of equality. I could ask you to write all of those steps out, and you should be able to at least verbalize what you did and what happened. But I'm not necessarily going to ask you to write that kind of thing down. So don't get too concerned about that. I just wanted to say that that is a possibility. Okay, let's do another one. And again, I'd like for you to try this one on your own after I've written it down. So after I've written it down, please pause and see what you can do on your own. And I did say I was going to use other variables besides x and theta. This one is secant of alpha. Alpha, lowercase alpha, and lowercase beta from the Greek alphabet, and theta are very frequently used for angles. When you have multiple angles, like if you have two, you'll call one of them alpha and the other one beta. And the third one, a lot of times you'll call it gamma. I'm thinking now of more of a scientific or advanced math kind of thing. And if you just have one angle, a lot of times we call it theta. And of course you can use all of them. If you had 4 variables, you could use alpha, beta, gamma, and theta if you wanted to. Anyway, so kind of get used to seeing the alpha and being able to draw it, because you'll probably see that in some problems. So practice drawing that. It looks like a fish, I suppose. That's the way I draw it. Well, it's real hard to tell when it doesn't do what I'm asking it to do. The pen, I mean. So kind of watch the stroke as I'm drawing the alpha, the order in which I do it. Start up here and just sort of make that fishy looking thing. Oh my goodness. I gotta write the problem down correctly. That's a minus. I had put another plus. Okay. Prove that this is equal to this. Okay, so which side do you want to start with? Sorry. It's just looking to see if I'd written something up above. Thought maybe I'd forgotten it, and I had not, so all's good. So which side do you want to start with? Hopefully you've come back after pausing and you're listening to what I say and maybe deciding how your proof looks in comparison to that. Well, I don't really care which one I start with, to be quite honest. I think they're both about the same. So I think I'll start with the left side. And in my head, I'm thinking, well, what is secant of alpha? What is tangent of alpha in terms of other things? I mean, that's kind of where my mind is going. And one of the things I'm thinking about is that they're all related to cosine. Remember that problem we did earlier that had the relationship of cosine was to both secant and tangent. And so that's kind of what our basic idea was. So I'm still thinking that is a good possibility. And so what I'm going to do, oh, actually, let me rewrite that differently. That's my first step. Instead of secant of alpha, I'm going to rewrite that as 1 over cosine alpha. So what I'm doing is I'm using a substitution. Basically, I'm writing everything in terms of sine and cosine. I'm kind of using that idea. Maybe this will make a lot of sense to you as to why I choose what I'm about to do. Do you see that every single one of those denominators of the little fractions is cosine alpha? Well, one way to deal with what's called a complex fraction, fraction that has fractions in it. I'm going to make one up over here. Okay, a fraction has fractions in it. What you're going to do to simplify a complex fraction is look at all of the little fractions at their denominators. I have b's and d's, and I'm going to find the common denominator, so that will be b times d, and I'm going to multiply the big fraction by that common denominator over itself as a form of 1. This is a technique for dealing with what are called complex fractions. Then I'm going to distribute b times d to each of these items. So when I multiply a over b times d, the b's cancel, leaving a times d. Plus, then I'm going to distribute the bd times c over d. The d's cancel, leaving b times c. Okay. Then I'm going to distribute in the denominator bd times e is bd e plus, and then I'm going to distribute bd times b over d. The d's cancel, leaving b squared. And what you have as a result is a fraction that does not contain fractions, and that's kind of the idea. So let's do that on this problem. What is the common denominator for all these fractions? Well, this is way easier than what I just did above. They're all cosine alpha, so the common denominator is cosine alpha. So I'm going to multiply by 1 in the form of cosine alpha over cosine alpha. When I distribute cosine alpha to the first fraction, I'll get 1. When I distribute cosine alpha to the second fraction, I'll get sine of alpha. In the denominator, 1 over cosine alpha times cosine alpha is 1 minus, and then I multiply cosine alpha times sine of alpha over cosine of alpha. I'm left with sine of alpha. Okay, now let's see. Now what I see is a 1 plus sine of alpha and 1 minus sine alpha. And so I'm thinking of using the conjugate, but the conjugate of which one? So think about it. What would you want to multiply the numerator 1 plus sine of alpha by to get 1 plus 2 sine alpha plus sine squared alpha? Or, on the other hand, what would you want to multiply 1 minus sine alpha by to get cosine squared alpha as a result? And if you've been paying attention, I'm hoping you're going to think this is pretty obvious, that the conjugate of the denominator is actually the one that's going to help me here. Because when you multiply the numerators, you're going to maybe use FOIL, as maybe what you think in your head when you do binomial multiplication, and you'll get 1 plus sine alpha, so 2 sine alpha, plus sine times sine, which is sine squared alpha. That should be looking good to you now, right? And in the denominator, when you multiply, you're going to get a difference of 2 squares. So 1 squared is 1 minus sine squared of alpha, which, if we use an alternative form of the Pythagorean identity, that's the same thing as cosine squared alpha, that denominator. So, is that what we wanted to get? Is that it? It looks perfect. That's exactly what we wanted it to be. So we can say, therefore, we now know that secant alpha plus tangent alpha divided by secant alpha minus, oh, I forgot to write the c there, secant alpha minus tangent alpha is indeed equal to 1 plus 2 sine alpha plus sine squared alpha divided by cosine squared alpha. Okay, so that proof is done. By the way, had we started with the other side, this is kind of an interesting thing. Sometimes if you start with the other side, basically you're just going to reverse what you did. So you might have started with this bottom part of the answer and realize that you could factor the numerator into 1 plus sine of alpha times 1 plus sine of alpha. And you may have thought, well, I can replace cosine squared alpha with 1 minus sine squared alpha, and that would factor into 1 minus sine alpha times 1 plus sine alpha. And then you could have canceled the 1 plus sine of alpha. So I'm not sure how you would have thought to divide. Instead of multiplying by cosine alpha over cosine alpha, multiply by 1 over cosine alpha over 1 over cosine. I'm not sure you would have thought of that necessarily. So maybe this direction we went was the best way to do it. But sometimes you can actually argue from the other side. It's just basically a reversal of the proof you did. And sometimes you'll think, I never would have thought of doing that for the reversal. So anyway, that's a proof of that one. Okay. Now, let's see. We have an example. Applying a Pythagorean identity to electronics. Tuners in radios select a radio station by adjusting the frequency. These tuners may contain an inductor L and a capacitor C. The energy stored in the inductor at time t is given by L of t is equal to K times, or K is a constant, times sine squared of 2 pi times F times T. And the energy stored in the capacitor is given as C of T equals K times cosine squared of the exact same argument of cosine. 2 pi F T is the same argument for cosine as it is for sine in the one above it, where F is the frequency of the radio station and K is a constant. The total energy, E, the total energy of the radio station, the total energy in the circuit is given by the equation L of t plus C of t. And they want us to show that E is a constant function. Okay, so we already know that E of t is equal to L of t plus C of t. So I'm going to use substitution, take the L of t out and put something that's equal to L of t in its place. Plus, and I'm going to, by substitution, take out the C of t and put something that's equal to it in its place. And I notice that K is a common factor. So I'm going to factor out the K. Okay, now, since those arguments are the same, it's 2 pi ft for both, the identity sine squared of theta, you might say the word something, plus cosine squared of the same something. As long as those arguments are identical, we know we have an identity for that, and it's equal to 1. So even if the argument is complicated, like 2 pi ft, as long as it's the same as the argument for the other one, that identity holds, and that means that sine squared of that plus cosine squared of that is equal to 1, and k times 1 is k, which is a constant, of course. That's the way it was defined at the outset. So we ended up being able to show that the e function is constant. It's equal to k, which is a constant. Okay, that finishes up the lesson for this section. I will see you in class.